In this video, I want to talk about the idea of continuity. And continuity is a very important concept in functions. It means that they're very, let's say, nice in the way that there's really no jumps. There's no real weirdness we have to deal with. This isn't quite true, but for most of the functions that you'll run across, you can think about continuous functions as functions that you can draw without lifting your pen off the paper. That's not quite true, but that's not a bad idea to keep in mind. There's a couple of subtleties about continuity where that idea fails, but most of all, that is true. And we'll talk about some of those subtleties in a little bit. But let's talk about what the definition for continuous is. It says that a function is continuous at a point A exactly when the limit at the point A is the same thing as the function evaluated at A. For example, if we had an A here, well, f of A, there's f of A, and you can see if we approach A either from the left or from the right, it looks like the y value approaches f of A. And that's kind of what's going on. The function value makes sense with the limit. That's the easiest way of thinking about it. And encoded into this, we have a couple of things. Well, it tells us, first of all, that the function exists at A. F of A exists. It also tells us that the left hand and the right hand limits also exist. And it also tells us that the left and right hand limits equal the function at A. So there's a lot of information in there. We can also talk about continuity on an interval. So we say a function is continuous on some sort of open interval. By an open interval, just as a reminder, so this is all x values between b and c, not including b and c. So there's a strict inequality there. So basically, this open definition is basically just the point definition at all points A in that interval. And we'll see on the next slide an example of this. But I want to talk about continuity on a closed interval first. So it's almost the same. As a reminder, a closed interval just includes those endpoints as well. So it's all things in the interval from B to C. But now instead of strict inequalities, where we let them be less than or equal to. So it could be B and C itself. So we say that a function is continuous on a closed interval when it's continuous on the open interval contained in the closed interval, so everything but the endpoints, and we just have to tack on what's going on with these endpoints. And there's a little bit different of a thing we have to do here. Because we're in a closed interval, and there's kind of nothing to the left of B and nothing to the right of C inside of our interval, well, we just take the limit from one side. We just approach B from the only way we can while staying inside our interval, so from the right. And we only approach C the only way we can from the left inside of our interval. And so f of B has to equal the limit here, and f of C has to equal this limit. I'll show you in a diagram on the next slide what's going on. So here's an open interval BC. And we have a function that's continuous over this open interval B to C. And the way to think about it is, for any point in here, let's start with, say, this point. We'll call that A. The limit and the function value line up. So the limit as we approach A from the left is f of a, and same with approaching it from the right. So there's no jumps or anything like that. It's a nice smooth function you can draw with your pencil. And you could think, well, what about points really close to the endpoints B? Well, that's fine. We can pick a point that's really close. But as long as we're not picking B exactly, we're not allowed to inside an open interval. It doesn't include B and C. Then there's always points even closer to B that we can pick to think about limits. So this works for all values inside our interval here, which is great. And then we can pick, again, we can pick something really close to C, but we're never going to pick exactly C in an open interval because it's not in there. Now if we're talking about a closed interval from B to C, so this includes the points B and C. Well, for all the stuff in the open interval B and C, which is everything but the endpoints B and C itself, well, the same thing just applies from the previous case. But if we think about what happens at B and at C, well, if we're just worried about this interval, there's no way to take a limit from the left here. There's no points to be able to go just a little bit smaller than B. They don't exist in that interval, so we can't do that. We can only approach from one direction. In this case, it's from the right. And similarly, with C, we can't approach from the right. We can only approach from the left. So when you're taking limits at endpoints of a closed interval, you just have to do the limits at one side, just because there's nothing in our interval over the other side to allow us to take that limit. We can't approach because that function might not even exist outside of there. We just care about what happens inside the interval that we're asked about. Okay, let's look at this function and talk about different types of discontinuities we could see. So, a quick note about the domain of this function. So I'm using kind of function notation talking about the domain and the range. The domain are all the values you're allowed to plug into the function, and the range is all the possible values that you could hit, not necessarily all the values we will hit with the function, but all the values you possibly could hit with the function. That's the range. So I'm going to say that this function f is defined just over the non-negative real numbers. So 0 and onward. So 0 to infinity. So I want to talk about a couple of points here. And so let's label these points. This is obviously 0. This point will be 1. This point will be 2. Maybe I'll do this in a different color actually. This is 0. This is 1. This is 2. And let's say this is 3. So, first of all, at 0, at x equals 0, this is continuous. So right here, we do have continuity. Since we have that the limit as x approaches 0 from the right, because that's the only way we can go, our function isn't defined to the left of 0 for negative numbers, so we can only take the limit from the right. So the limit of our function equals f at 0. When I plug in 0 into my function, in this case I get 0, and that's what the limit approaches. So we have that this function is continuous at x equals 0. Now, these points here, 1, 2, and 3, we have some discontinuities. So at 1, you can see that the limit from the left does not equal the limit from the right. So this is called a jump discontinuity. Because the limit as x approaches 1 from the left of f of x doesn't equal the limit as x approaches 1 from the right of f of x. However, if you wanted to, you could say that this is kind of continuous from the right here, since as we approach from the right, we do get the limit being the same thing as the function value at 1. So this is f of 1 here. So that equals f of 1. So we can say it's continuous from the right, but not from the left in this example. But the whole point is this bit shows a jump discontinuity. We'll call this an infinite discontinuity at x equals 2, since we have that f of 2 exists. In fact, it equals 0 in this case, because we have a dot there. But it doesn't equal the limit as x approaches 2 of f of x, because that's negative infinity. So this type of discontinuity is called an infinite discontinuity. And the third type here is called a removable discontinuity. And I'll explain this in a second. And the reason it's called a removable discontinuity is because we can remove it by redefining what f of 3 is. If we changed the value of f of 3, if it was no longer here, if we changed it to be, I'll color this in a different color, maybe I'll do it in yellow. So if it's no longer here, if we instead decided to put it there, right on the function where it should be to be continuous, then the function would be continuous. The other two examples, you can't do that nice redefining one point to make it continuous, so these are not removable discontinuities, but this guy is. So continuous functions at a point A behave very nicely when you perform arithmetic on them. They, in fact, stay continuous at those points. So if you have continuous functions f and g, and they're continuous, let's say, at this point A, then you can add and subtract them, and they're still going to be continuous at A. You can multiply a function by a constant, it's still going to be continuous at A. You can multiply these two functions together, and that multiplication is still going to be continuous at A. You can divide those functions, and that's going to still be continuous at A. There's a little wrinkle here. We just have to make sure that g of A, that value that both the function takes and the limits approach, is not 0, because we can't divide by 0. That's all this is saying. So in some sense, continuity behaves very, very nicely. And in fact, it's pretty easy to see that a constant function, let's call that constant function k, so f of x equals k, is always continuous. So it's continuous at A. And so is f of x equals x. That's, of course, also continuous. That's just a straight line diagonally. So what does that mean? Well, if we know we can add, subtract, multiply, and divide, and multiply functions by scalars, and we have these two functions, well, we can make any polynomial we like out of these guys using 1, 2, and 3. And using 4, we could take two polynomials and divide them, and we have division. So we have that polynomials and the ratio of two polynomials, or rational functions, are continuous. We'll have to be a little careful here, everywhere they're defined. Something like 1 over x isn't defined at 0, so it's not even part of the domain of the function, so we're not really worried about it, but anywhere where you can plug in a value into your function and get out a value, it's going to be continuous there. So let's look at the following function. We have f of x equals 3x squared minus 2x plus 1 over x squared minus 5x plus 4. So this is a rational function since it's two polynomials that are divided by each other. So using the material on the previous slide, we know that this is going to be continuous at every value that it's defined for. And so if we have a rational function, it's going to be defined at all values except for when the denominator is 0. So we can do a little bit of work to simplify this. The numerator really doesn't matter. 3x squared minus 2x plus 1. But the denominator we can factor. We need two numbers that add to give you, multiply to give you 4 and add to give you minus 5. So minus 1 and minus 4 will do it. X minus 1 times x minus 4. So this is 0 exactly when x is 1 or x is 4. Or I should say the denominator is 0 exactly when x is 1 or x is 4. So we know that our function, f of x, its domain is all of the real numbers, but not the numbers 1 or 4. We're not allowed to plug those in. That's the natural domain of this function. And by the previous slide, we say that f of x is continuous on all real numbers except for 1 and 4, where our function isn't even defined. In fact, it has some asymptotic behavior going on. I'll just sketch this very quickly. So our function looks something like this. So if this is 1 and this is 4, then our function looks something like this. So it starts going up there, and then it comes down, and then it comes down like that, and then comes off there. And you can see it has these asymptotes at 1 and 4. So we know the function doesn't even exist there, so it's not in the domain. And what also is nice is kind of all of the functions that we run into in our mathematical career, for the most part, all the nice ones, are continuous everywhere where they're defined. So all of your trig functions, so e.g. sine of x, which is defined everywhere. You can plug in any number you like into sine and you'll get some value between -1 and 1. Or something like maybe tangent of x. So you can plug in any value into tangent of x that you like. That isn't a value that makes cos of x 0, for example. But any of these are all continuous where they're defined, which is excellent. Exponential functions as well. 2 to the x, or e to the x, or pi to the x, or whatever. Or logarithmic functions, maybe log base 10 of x, or log base e, or the natural log of x, or whatever. So all of these nice functions that we deal with are continuous everywhere where they're defined, which is very, very nice. So basically we know if we see a function that we use kind of every day, there's a good chance it's going to be continuous. Continuity is really nice as well under composition. Basically, as long as the function in the inside of your composition is continuous, and the outside function is at the value of the inside function, then you're good to go. Let me give you an example. Let's look at sine of x squared minus 3x, and we're going to see if that's continuous. I'll use CTS for continuous, at, let's say, x equals 4, question mark. And, well, the solution, well, we know that our inside function, that's continuous at every value. So, I know that x squared minus 3x is continuous at 4, so 4 is like our a in this case. And our inside function, x squared plus 3x, is our g of x. And now what does this evaluate to? So if we plug in 4, we know the limit is the same as the function value since it's continuous. So we can plug in our function value here. Or maybe I'll write it like this. 4 squared minus 3 times 4. Well, that's 16 minus 12 is 4. Well, that function evaluates to 4. It happens to be the same value, but that's just a coincidence. So that's our f of a here. And we know sine of x is continuous at x equals 4. That's our f of a. So we know the composition. What we started with, sine of x squared minus 3x is continuous at x equals 4. And that's how composition and continuity plays with each other. All right, let's look at this function. So we want to find where this function, f of x, which is the square root of cos of x, is continuous. And we can view this as a composition of functions. So we can say maybe the outside function is the square root of x, and the inside function, g of x, is cosine of x. So then we have, if we take g of x and we plug it in to f of x, well, rather than having f of x is square root x, we'll have f of g of x is square root g of x. Maybe I'll write this in 2 steps. Square root g of x, since we're plugging g of x into our function, but g of x is just cosine x. So we can see that we have a composition here. Now, what do we know about the square root of x? We know square root x is continuous. On its domain, wherever it's defined. But when can we take the square root of a number? As long as that number isn't negative. So, the domain of the square root of x is everything but the negative numbers. So from 0 all the way to positive infinity. So we know that. And we also know for g that cosine of x is always between -1 and 1. And that's kind of the idea here. So we just have to figure out where cosine of x is not negative, since we're plugging that in to a square root. So whenever that indeed exists, we're good to go. Let's do this on the next slide. So here's a graph of cosine of x. And remember, we want to exclude where cosine of x is negative because we can't plug negative numbers into our square root function. So the stuff in green is the stuff that we want, and the stuff that's not going to be in the green is the stuff we don't want. And remember, I just drew a piece of this. This goes on forever, just oscillating between 1 and -1. And in terms of the unit circle, well, remember, cos is the x value of angles, so it's all angles that are on the left half of the circle. So all of this is the interval we're looking for. So how can we write this? Well, we can maybe say this angle here is pi over 2, and this angle let's call it negative pi over 2, I guess. So any angle that we like between pi over 2 and negative pi over 2 is going to have a non-negative cosine value. And we can graph them here. This here is pi over 2. This here is negative pi over 2. And then, well, we can take as many trips around the circle as we like. So it can be pi over 2 plus 2 pi plus 4 pi plus 6 pi plus 8 pi, or we could go in the negative direction, minus 2 pi, minus 4 pi, minus 6 pi, minus 8 pi, all the way to however many multiples of 2 pi you like, either positive or negative. So we can say that cos of x is greater than or equal to 0 when x is in the following interval. I'll write it like this first. I'll leave some space. And it's going to be a closed interval because we can plug in pi over 2 or negative pi over 2 and we'll get 0. But 0 is fine to take the square root of, so we do have a closed interval. So we have when x is between, remember we put the smaller thing on the left, pi over 2, and I'll leave some space for a second, and positive pi over 2. So negative pi over 2 and pi over 2. In fact, I'm going to put a little more space here. I think I need just a little more. But remember, we can get an equivalent angle to this angle, let's call this angle theta, by going around the circle as many times as we like. So this is the same thing. We'll say it's equivalent, or maybe I'll do it down here. This angle here is equivalent to theta plus or minus n copies of 2 pi, where n is whatever integer you like. So we're just going to include that in our interval as well. So it's going to be plus n times 2 pi on both of these. And I'll tell you what n is, where n is whatever integer you like. So any angle that you're drawing on a circle where it goes through kind of the right half of the circle, or it touches the right half of the circle, or the top and bottom, they are fine to put in here. From the previous slide, we know that cos of x is continuous everywhere, but we don't want it to be negative because the domain of the square root of x is just non-negative numbers, so we can't plug in negative numbers. So, talking about continuity, we know that the square root of cosine of x is continuous. I'll just write CTS for continuous whenever it's defined. And it's defined on all values x where cosine is non-negative. So let's say the intervals negative pi over 2 plus n times 2 pi all the way to positive pi over 2 plus n times 2 pi. And that's what's going on here. So these intervals, which I'm going to highlight in red up here, any x value that we plug in there is good, that we plug in there is good, that we plug in there is good, etc. This goes as far to the left and as far to the right as we like. And just to make sure we understand these values, well, if this is pi over 2, this value here is going to be minus pi over 2 plus 2 pi, because it's the left-hand side of our interval. So that's going to be 3 pi over 2. So anything from 3 pi over 2, and then pi over 2 plus 2 pi here is 5 pi over 2. And we could do that, keep going, so the interval from 7 pi to 9 pi, the interval from 11 pi to 13 pi, etc. And in the negative direction, let's just write down the first couple here. So the same thing, this is going to be negative 3 pi over 2. This is going to be negative 5 pi over 2. So just taking the interval of all the numbers between negative pi over 2 and pi over 2 and adding integer multiples of 2 pi to it, just because that's just going around the circle a bunch of times. Whatever n is, that's how many times you're going around the circle, and then calculating your angle. So anyway, here is the entire domain of our function, the square root cosine of x. And since square root of x is continuous everywhere it's defined, and cosine is continuous everywhere it's defined, and we have a composition of these functions, well, we just needed to figure out where it was defined, which was this family of intervals here in red.